Hi everyone, and welcome back to my flight mechanics class. Today we're going to cover the longitudinal static stability, and that essentially means, is the aircraft stable in pitch? So the first thing that you should know is that there are two types of stabilities. There's the static stability and the dynamic stability. Static stability refers to the aircraft's initial tendency to return or not to return to its steady state following a disturbance. Dynamic stability refers to the subsequent motion in the longer term, that is, whether the oscillations grow, stay constant, or shrink over time. Now, both thrust and aerodynamic forces have an impact on pitch stability, but today we're going to focus on drag and lift only. Essentially, what you need to understand is that the sizing and location of the lifting surfaces, as well as the center of gravity location, will greatly influence the overall pitch stability, as they will determine the pitching moment of the aircraft. Longitudinal static stability is all about the pitching moment and the general equilibrium created by the interactions of the thrust and aerodynamic forces. So static stability can be positive, neutral, or negative, and that is positive when the aircraft returns to its steady state, neutral when it doesn't do anything, and negative when it diverges from it. So let's start with the first parameter. The first parameter is drag, and up to now it was defined as D only. So we're going to go a step further and express it in terms of its coefficient, and that is the drag coefficient times the dynamic pressure Q bar times the reference area S. And we can see that the drag coefficient can be further broken down into a series of sub-coefficients, and that would be CD0 star plus CD alpha alpha plus CD IH plus CD delta E times delta E. CD0 star is equal to the drag coefficient when alpha, IH, and delta E are equal to 0. Alpha is the angle of attack, IH is the incidence of the horizontal stabilizer, and delta E is the elevator's deflection. So the first thing that we're going to do here is a simplification, and that is that anything that comes after alpha is going to be considered negligible. So the drag coefficient is really equal to CD0 star plus CD alpha alpha. So now the question is, how do you find CD alpha and CD0 star? And the answer lies in the drag polar. Usually the drag polar is depicted as the lift coefficient versus the drag coefficient. But in this book, it's depicted as alpha versus the drag coefficient. And it essentially measures how sensitive to alpha your drag coefficient is going to be. And what we want to do here is to linearize the drag polar at a steady state alpha, in this case alpha 1, and then the slope of that curve is going to be equal to CD alpha. CD0 star can then be found graphically as shown at the bottom of the image. So the first thing we need to do is to start with the general equation for the drag polar. And the first parameter, CD0, is essentially equal to the friction drag. That we can assume to not be dependent on alpha. The next parameter, CL squared over pi E AR, is essentially the induced drag. Induced drag is the drag that is created as a byproduct of creating lift. So the more lift you create, the more induced drag you're going to have. And that is very much correlated to alpha. So what we essentially need to do here is to take the partial derivative of CD with respect to alpha, and that is going to give us our CD alpha. And if we assume that CL is equal to CL alpha alpha, then CD alpha is equal to 2CL times CL alpha over pi E AR. As a clarification, E is a measure of how efficiently distributed your lift is on your wing, and AR is the aspect ratio. So when you take the derivative, CD0 goes to 0 because it's not dependent on alpha, and then the derivative of CL squared is 2CL times what's inside the parenthesis, and that is CL alpha. And that is the reason why you see what's at the bottom. So this is going to be our CD alpha, and then the CD0 star can be found graphically. So now the next parameter is going to be lift. Lift can be defined in terms of its coefficient, and that is the lift coefficient times the dynamic pressure Q bar times the reference area S. And just like the drag coefficients, it can be further broken down into a series of sub-coefficients. And that is CL0, CL alpha alpha, CL IH times IH, and CL delta E times delta E. So you can see that the lift coefficient actually depends on the same parameters as the drag coefficient. And the aim here is going to find these sub-coefficients to derive them. So the first thing that you should know is that lift cannot be treated as a single parameter. And the reason for that is because we have two lifting surfaces. We have the main wing and we have the horizontal stabilizer. So we need to find the lift for both of these surfaces. And for that to happen, we first need to find the angle of attack alpha for both of these lifting surfaces. So for the main wing, alpha wing is actually equal to alpha plus the incidence of a wing. For the tail, you're going to have what's called a downwash. And the reason for that is because the main wing actually propels the air downward. And what this essentially does is that it artificially reduces the angle of attack at the tail of the aircraft. And that is reduced by an angle epsilon, as shown on the image. So epsilon is equal to epsilon 0 plus d epsilon over d alpha alpha. And this is something you would be able to figure out with wind tunnel testing. So your alpha at the tail is going to be equal to alpha plus the horizontal stabilizer's incidence plus tau e, the elevator's effectiveness, times delta e, the elevator's deflection, minus epsilon, your downwash angle. So the elevator's effectiveness is essentially a measure of how much of a change in alpha you're going to get for a change in delta E, and this is your tau E in the equation. So the next thing that we need to do is to compute the total lift for the aircraft, that is the lift of the main wing and the lift of the tail. So if you wanted to be precise, you would have to take into account alpha in the scalar equation. Basically, you're going to be computing a scalar equation for the total lift of the aircraft. And if you want the vertical components, you would have to multiply the lift of the main wing times cosine of alpha, and the lift of the tail times the cosine of alpha minus epsilon. And the reason for that is because the lift of the aircraft is perpendicular to the incoming air velocity. And to compute the vertical components, you have to account for the angle of attack and the downwash angle. So the downwash angle, as you can see, it essentially tilts the lift vector backwards because it's an artificial reduction in the angle of attack. So the book actually makes a simplification, and that simplification is that alpha can be considered to be very small or negligible, and that means that the lift of the main wing is actually considered to be equal to the vertical component of the lift of the main wing. And for the tail, you would have to multiply the lift of the horizontal stabilizer times cosine of epsilon. And this is what you see at the top. You see that the total lift is equal to the lift of the main wing plus the lift of the tail times cosine of epsilon. And there's an additional simplification that's being made here, and that is epsilon is very small, so the cosine of something very small is equal to 1. So your total lift is actually equal to the lift of the main wing plus the lift of the horizontal stabilizer. Now the next thing that we can do is to express all of that in terms of their coefficients. So the lift coefficient, the total lift coefficient, times the dynamic pressure times the reference area is equal to the lift coefficient of the main wing times the dynamic pressure at the main wing times the reference area of the main wing plus the lift coefficient of the horizontal stabilizer times the dynamic pressure at the tail times the platform area of the horizontal stabilizer. And as a way to rearrange that, what you can do is divide everything by Q bar S. And what you get at the bottom is the lift coefficient of the main wing plus the lift coefficient of the horizontal stabilizer multiplied by the dynamic pressure ratio times SH over S. And this is the main equation that we're going to use to derive the sub-coefficients of our lift coefficient that we saw on the first slide pertaining to the lift of the aircraft. So what we're going to do here is we're actually going to expand the lift coefficient of the main wing and the lift coefficient of the horizontal stabilizer. And we see that they're equal to CL0 of the main wing plus CL alpha of the main wing times alpha of the main wing. And then for the tail, it's equal to CL0 of the horizontal stabilizer plus CL alpha of the horizontal stabilizer times alpha of the horizontal stabilizer. So we can assume the incidence of the main wing to be equal to 0. So alpha wing is actually equal to alpha, and alpha of the tail is going to be equal to what we had derived a few slides earlier. And what we do here is we essentially take the equation at the bottom here and we plug in everything that we have found, and that is the expansion of the individual lift coefficients in addition to alpha of the horizontal stabilizer. And what you would get is what's at the bottom of the slide. So now to find the individual sub-coefficients making up the lift coefficient, what you need to do is to take the partial derivative of that equation at the bottom with respect to alpha, with respect to IH, and with respect to delta E, and you will find your sub-coefficients CL alpha, CL IH, and CL delta E. As for CL0, what you need to do is to take the equation at the bottom and you set your alpha, IH, and delta E all equal to 0. And what you would get is what's seen here on this slide. So at the top, when you set your alpha, IH, and delta E equal to 0, this is what's left. And then for the three following equations, these are basically the partial derivatives of the equation at the bottom here with respect to alpha, with respect to IH, and with respect to delta E. And this is what you would get. So this is it for today. And next time we're going to dive into the pitching moment of the aircraft and what it should be in steady state flight. Thank you very much. See you next time.